Hey, so on this one here, we're going to be looking at, I believe, page 20, problem number 55. And if you actually want a review of this, go back to page 15. We are going to work with an idea called points of intersection. If you think about graphing lines on an XY plane, at some point right there, they're either going to intersect one another, and it's possible that they don't intersect, right? When we have two lines that never intersect, we call them parallel lines. The neat application about parallel lines is that they have the same slope. If two lines have the same slope, they will never intersect. Now, if two lines do not have the same slope, then we have the idea that they are going to, at some point, intersect, right? If they intersect, they're going to intersect at one spot. Now, we do have this idea of coinciding lines, but a coinciding line is basically lines that are exactly the same, but they're kind of hidden under another identity. In other words, they have some sort of multiplier, like 2x plus 4 is sort of like the same as x plus 2 in terms of functions, or rather in terms of graphing lines, because the 2 can just be divided out and you have your x plus 2. All right, let's move back into this. On page 15, we have the idea of points of intersection. This helps us out with profit models. Now, when you work with profit models, you have to understand cost and revenue. Cost tells you how much you're going to get, how much money you're putting into the product, and revenue tells you how much you're digging yourself back out. The question is, when does something become profitable? And that's why we need to understand intersection points, is because here in this instance, we have our break-even point. Our break-even point will tell us when we will start making money on a unit, and it'll also let us know when we will be losing money on a unit. So let's take a look here at number 55. It says you are setting up a part-time business with an initial investment of $21,000. So think about this on your end. If you are investing, you are giving away $21,000. So you're not making money on that $21,000. So if we're thinking about this in terms of trying to generate a profit, the investment is going to cost you on the front end. So $21,000 investment is going to go as part of the cost. Let's go ahead and start breaking that down here. We have a $21,000 investment that's going into our cost. It goes on to say that the unit cost. So again, notice that anytime you see the word unit in any situation, think of the number 1. Why do we do that? If you have a unit, you are referring, when I'm talking about graphing, I say 3 units. I just mean that we're going to move over 3 ticks. Each tick is a unit. Each one is a unit. The unit circle that you work with in geometry and trigonometry has a circle with radius 1. The unit square is a square with a side 1 by 1. So unit means 1. In this case here, the cost of one item is $11.50. So think about that. If the cost of one item is $11.50, the cost of 2, right, is $23. The cost of 4 is $46. In general, though, we don't know how many we are making. So that's going to be our variable there. How many are we producing? That is to be discovered. We don't know yet. That's our unknown. So the unit cost, $11.50. Now it goes on to tell us here the selling price, how much we are going to sell that unit, is $19.90. So that's actually going to go into our revenue. We want to make money. We want to generate, as a company, we want to generate revenue. So over here, we're going to start tacking in our revenue. So we're going to sell it for $19.90. It says here, find equations for the total cost and the total revenue for X units. Again, we said before that we don't know how many units we're working with. If you don't know a number, use a variable. So X units. We're going to let X equal the number of units. When you work these mathematical problems, when you work with variables, to understand, when the reader is looking at this, what does X represent? Let X equal the number of units. Now I know for every formula, for every equation, what does X represent? It's a variable that represents the number of units. In this case right here, how much is the cost? We are investing $21,000, but notice here that we also have a cost of $11.50 for each unit. So how do we determine that cost there? It's $11.50 for each, but how many do we have? We have X number of units. So how do we configure that cost there? For each unit, it's $11.50. So we want to multiply, right? $11.50 times X. If we have 6 units, then we'll take the 6 units, multiply it by the unit cost. But that isn't our total cost, is it? We also invested $21,000. So we must add in that investment of $21,000. That is our cost equation. And just to give you that idea, since we have been talking about functions, the cost depends on the number of units sold. So cost here, C, depends on X. So this is a function where C depends on X. So let's write this in function notation. C of X, right? Our cost function depends on the number of units sold. What about revenue here? Think about revenue. Now, revenue is always going to follow the same formula, and this is in the back book of the book if you'd like to take a look at it, and some extra formulas for business and economics. The revenue says how many units do you sell and at what cost. Multiply that together, and you have your formula for revenue. So if we sold X units at $19.90, multiplying the two together, we will have our revenue function. So revenue depends on the number of units sold. So revenue denoted R, R of X says we have a revenue function that depends on the number of units sold. We're selling for $19.90, and we are going to multiply that by X, the number of units sold. So we have our revenue and our cost function. But part B, and if we want to, we can go ahead and check that. As you see below, there is an answer selection. It says here that C, our cost equation, is the $11.50 plus our $21,000. And our revenue equation here, we're going to take the $19.90 and multiply it to our number of units sold. Moving to part B, find the break-even point by finding the point of intersection. Now, as we said, mathematically speaking, the point of intersection, sorry about that, everyone. The point of intersection is where the two graphs are equal to one another. It's where they cross, right? It is where they intersect or where they cross on the graph. So that means we are looking for that specific ordered pair where it is equal to, or that it agrees for both of the equations. The way that we can find that is just by setting cost and revenue equal. When does cost equal revenue? That will tell us our break-even point. In other words, at the beginning here, as you see, we invested a lot of money into this. So we start off in the hole. We have negative money right now. But the more revenue that we generate, we are actually going to gain profit. So when do you start gaining profit? Well, think of it like this. If you have more revenue than you do cost, you have profit. If you have more cost than revenue, you don't have profit. You have a negative profit. If the revenue is larger, you have positive profit. So that's a good thing. However, when cost equals revenue, you have a profit of 0. That is your break-even point. When profit is 0 or when revenue equals cost, you find your break-even point. So what we're actually going to do here is we're going to take the cost equation or our cost function, and we will set it equal to our revenue function. There you go. We have our break-even point when our revenue equals our cost. Let's go ahead and try that out here. Let's set revenue equal to cost. The 19.90x equals our cost of 1150x plus 21,000. So notice here that when we set these two equations equal to one another, we took a linear equation and set it equal to a linear equation. So now we're just going to look to solve for our variable x. How can we get x together? Well, we need to somehow combine these two terms here that share the variable x. This number is a little smaller, so I'm actually going to consider moving it over here on this side. Subtracting the 1150 times x to each side. Notice that we can do this here because they are like terms. We have x to the first power. So we can combine these two by subtracting what we call the coefficients, the numbers in front of x. 1990 minus 1150, what does that give us? $8.40 multiplied by the number of units sold. This equals the 21,000. To get x by itself, we divide by the 8.40. And so actually I'm going to show you on Desmos how we could work with finding this value here. Well, I thought I could. There we go. Looking at this here, 21,000 divided by 8.4. 21,000 divided by 8.4. And it didn't like that. So it says here we have approximately 25. Let's see here. That is correct. And I had to make sure on my paper to make sure that everything looked good. I was looking off in the wrong spot. Not even gonna mess around with that one. Okay, x equals 2,500. But I'm gonna go ahead and minimize this here. But what does that mean here for us? What does that mean here for us? X equals 2,500. That's the number of units. X is 2,500. X is 2,500. That's the number of units. So that tells us we must sell 2,500 units in order to break even. If we sell less than 2,500 units, we will lose money. We will have more cost than revenue. If we sell less than 2,500 units, we will lose money. If we sell more than 2,500 units, we'll make money. There will be profit. We will have profit if we sell more than 2,500 units. The break-even point when revenue equals cost, 2,500 units. You will not lose money there. Anything lower, you lose money. Anything higher, you actually gain money. And it goes on to say here too, well, how much money would you actually have at that point? How much money would you have sunken into it? We'll take the 2,500 and plug it into either one of these equations, and it'll give you the idea of the amount of money that you will have generated and it will cost you for 2,500 units. Let's take a look at that. Let's take 2,500 and multiply it by the 1990. Let's go back to our calculator. 2,500. If we have 2,500 units and we sell them for $19.90, how much money would that be in revenue? We see there that it is $49,000, or excuse me, $49,750. So if we sold 2,500 units, we would have a revenue of $49,750. What about the cost here? So we invested $21,000, but then we had the cost for each unit. For each of those 2,500, for each of these 2,500, it cost $11.50 to make. Notice again here, it did not matter which of these equations we worked with, revenue or profit, or excuse me, revenue or cost. The revenue equation said at 2,500 units, the revenue is $49,750. At 2,500 units, the cost is $49,750. So we can see there, they're exactly the same. So what is our break-even point? At $49,750, we must sell 2,500 units in order to break even. That's what we're working with there. Part C says how many units would yield a profit of $1,000. Now here's where it all changes, because we said here that the profit, if it's positive, or excuse me, if revenue is more than cost, we have profit. So how can you find this? How can you find this out? How many units would yield a profit? In order to find that out, you need a profit equation. How do we find the profit equation? Well, very simple. Our profit equation, profit, will be denoted P of X. Again, the capital P is profit. We're going to change it into a function as we go along. And the profit function can be found by taking the revenue function and subtracting the cost function. So this R of X here, 1990, we will subtract our cost function, and I want to put it in parentheses. I'm subtracting a bunch of stuff over here. I don't want to get the negative confused. I don't want to just make this negative. I want to subtract everything over here. So I'm going to subtract 1150 times X plus 21,000. Well, again, here, like terms, 1990 minus 1150X, we're going to get the 8.4X. I erased it. But what about right here, this $21,000? I cannot leave this positive. I had this mistake so many times last semester, and I really want to stress this here. This $21,000, we are subtracting 21,000. So this must be minus 21,000. Here we have our profit equation or our profit function. 8.4x minus $21,000. Now it says here, how many units? They don't know how many units. They want you to solve for x. What is x when profit is 1,000? Remember, that's what this relationship is here. What is the relationship between profit and the number of units? Here, they're giving you in part C, a profit of 1,000, what is x? What's the number of units? So to find this answer for part C, we are actually going to solve for x. We will take the 1,000 and plug it in for P. So what is x? What is x when this equation equals 1,000? So now we look to solve for x. Adding over the 21,000. So again, going back to my calculator, if I take the 1,000 on the left-hand side and I move over the minus 21,000 to the left-hand side, it's now plus 21,000. But now I have 22,000 equals 8.4x. So again, as we see there, to get x by itself, let's divide by the 8.4. 22,000 divided by 8.4. Notice what we get over here on the side. We get 2,619.047. Remember, this represents the number of units. We just solved for x here. X here is 2,619 and rounded off 0.047, 0.048. It's asking for number of units. How can you break down units? 1 unit, 2 unit, 3 units? Right? You wouldn't say 3.5. You wouldn't want to sell 3.5 t-shirts. It's either 3 t-shirts or 4 t-shirts. When we talk about number of units, that must be a natural number. Do you have 5 units? Do you have 10 units? You'll never have pi units or 15/4 units or anything like that. So these do need to be whole numbers. So the question here is, do I round down or I round up? It wants to know a profit of 1,000. If you round this number down to 2,619, then you will get a profit that is actually less than 1,000. Try it out. Take that number 2,619 and plug it in right here and see what you get. You will get a number just under 1,000. For that reason, we want to round up. 2,620. Again, if you plug in 2,619, you will get a number less than 1,000. Rounding it up to 2,620, you will have this many units to produce a profit of $1,000. This is problem number 88 on page 33. I like this one here because I think it kind of rounds off slope quite nicely. It says here personal income, and this is measured in billions of dollars, was 12,430 in 2008 and 14,167 in 2013. Notice again here what's going on in this problem is that we are finding a relationship between personal income and time. Notice it's giving us years, 2008, 2013. So there's a timeline being established. A timeline, that's a good thing for a horizontal axis, is to have a timeline. I'm already thinking about that. This x-axis here is going to work as a timeline. Let's see what the timeline is. It says also personal income, so that's going to work as our vertical axis. So there's our X and Y variables. What is the relationship between X and Y? It's our timeline versus our income here. It says that we are given information for each. Let's establish ordered pairs. It says, assume that the relationship between the income and the time is linear. We are establishing a linear relationship, so we should be able to find a linear equation given the information to us. It says, let 0 represent the year 2000. So if the year 2000 is 0, then the year 2008 is 8. So this timeline here, this X, they're saying use the variable t. There's nothing wrong with that. This timeline here, normally speaking, when you have applications, t is normally the horizontal axis, and that is our independent variable, so it is the x-axis. Okay, so t equals 8, and we also have t equals 13 for 2013 as well. So the first ordered pair, 2008, let's go ahead and establish the ordered pair, 8, comma, 12,430. Right, that is an ordered pair that shows the relationship between the year 2008 and the personal income of 12,430. Now remember, that's represented in billions. 12,000 billion dollars, what does that mean? That's more like $12 trillion, I believe. If you have 12,000 billion dollars, you wouldn't say thousand billion, you would just say trillion. So this is really $12 trillion, I think. I could be wrong. Don't quote me on that. Okay, moving on to the next one, 2013. That is the year with T13, and then our Y coordinate there, 14,167. Hopefully my numbers are not off there. Everything seems to look good. But what have we done here? We are told that there is a linear relationship. To have a linear equation, we need a slope. How do you find the slope? Well, look at these two ordered pairs that we just created based on our information. Let's use these ordered pairs here. Our slope here, the change in the y variable, so this 14,000 and 12,000, let's look at their difference. Let's divide that by the change in the t variable, 13 minus 8. So subtracting the top numbers here, we get 1,737 divided by 5. Now, again, when you divide by 5, you always end up with either a perfect number or some sort of decimal ending in 0.2, 0.4, 0.6, or 0.8. Those are terminating. Those are very, very nice decimals to work with. So you don't necessarily, see, this is simplified, right? That's a simplified fraction, but it's very messy to work with. Luckily for us, dividing by 5 is very friendly. If you divide by 3, 6, 7, 9, those numbers, it gets really rough. Dividing by 2, 4, 5, these are very nice numbers because any number that's divisible by 100, it's really easy to work with them out of fraction form. If they're not divisible with 100, then it gets messy. Okay, so this actually can be rewritten as 347.4. And again, remember that this is measured in billions of dollars. So this here is $347.4 billion. All right, so that's our slope. What does the slope tell us? For each year, after each year, our personal income is decreasing ours, right? The personal income here is decreasing by $347 billion. Now, what would this look like graphically? We already have our 2 points. Let's just go ahead and graph these on our XY plane over here. We move over 8. We move over 13. We move up 12,000. We move up 14,167. And again, I'm just drawing this kind of to scale, or rather not to scale at all, just kind of giving you an idea of what's going on here. Of course, we say that these lines are never ending, right? This line is going to continue. At least I hope so. I hope this world continues for us. But notice that says we're going to start at t equals 0, meaning 2000. It's very possible that they don't have any data before 2000. Now, graphically speaking, this line, we could extend and say, well, what if we did have a company back in the 90s or whatever? You know, it's just not realistic. They're starting at t equals 0, so at some point that 0 is going to clash over here. But let's again see what is the equation that we're working with. We have a picture. We have some information. We know these two ordered pairs are solutions to the equation. we know that this is the slope. So using this slope value and using one of these ordered pairs, we can actually find our linear equation. Let's try to do that. So once again, I'm going to use the slope-intercept formula. I'm going to take the slope and one of these ordered pairs, and I'm going to plug it in to y equals mx plus b. Using this first ordered pair, the y value, 12,430. So y equals mx plus b. M was 347.4, if I'm not mistaken. And the x variable, we actually changed to t. But what are we going to use for that? The value of 8. Solving for b, we will now have b and the value for m, and we'll have our linear equation. 347.4 times 8, and then solving for y here. We get that b is equal to 9,650.8. So again, multiply this by 8, subtract from the 12,430, and you will have your value of b. So what is our linear equation now? Y equals mx plus b. M is 347.4. We change the variable x to the variable t. Our value for b here, 9,650.8. So we have now an equation, algebraically, that represents this graphical interpretation of our equation. And it says here, estimate the personal incomes in 2011 and 2014. Well, how do we do that again? 2011, remember the year 2011 says, let t equal 0 for 2000. So let t equal 11 for 2011. Let t equal 14 for 2014. And for each of those, plug them into your equation and generate a y value. The y value represents the personal income. So you will be able to find the personal income in 2011 by plugging 11 into the equation. You will find the personal income in 2014 by plugging 14 into the equation. Last problem here for the linear equations, linear functions section. This is in 1.3, number 91, page 33. It says here, as a salesperson, you receive a monthly salary of $2,000 plus a commission of 7% of sales. You are offered a new job at $2,300 a month plus a commission of 5% of sales. So immediately off the bat, we have a current job and we have a new job. The current job does not pay as much monthly wage or monthly salary, but notice that the commission is slightly higher. So there could be some shift there in pay as time goes on. Again, the new job is going to offer you more upfront, but the commission is a little bit less in the back end. So again, understanding which one will pay more, that's what we're going to take a look at here. Part A says write linear equations for your monthly wage, represented by W, in terms of your monthly sales for both your current job and your new job offer. So let's go ahead and write this down, get the information where we need. I'm going to write current for the current job, and I'm going to write new for the new job offer. Current job pays $2,000, but then it says plus, right? Plus 7%. Now, when we say 7%, we're not going to plug in 7, right? Percent means divide by 100, right? Century per divide, 7 divided by 100. So that's the decimal, 0.07, right? That is the 700ths decimal or the 7 over 100 fraction. And it says it's 7% of whatever your sales are. Well, the sale is what's going to change, right? Your sales numbers are going to change. So we're going to let that be represented by the variable S, right? S is your monthly sales. All of this tells us the wages for our current job. Notice that our wages follow a linear equation. This is acting as our slope because this is what's changing. For each sale, we get 7% commission. For each dollar on the sale, we get a 7% of that dollar. So 7 cents on the dollar we get back. What about the new job? New job says we'll pay you $2,300 a month plus 5% of your sales. 5 divided by 100, 0.05. We have these two linear equations representing the sales, or wages, excuse me, representing the wages of our current job and this new job offer. So we have our two equations. Part B says use a graphing utility. Let's go ahead and actually use algebra to find the point of intersection. Well, how do you find the point of intersection? You set the equations equal to one another. Why are we allowed to do that? Well, what does it say here? W equals this. W equals that. If it equals this and that, then they're the same. Let's see what happens. Setting 2,000 plus 7% of S equals 2,300 plus 5% of S. So notice again here, our variables and our constant numbers. We want to combine our like terms together. So we're going to start off here by subtracting 2,000 from each side. If I subtract 2,000 here, it's gone. If I subtract 2,000 here, I get 300. Now what about these? I need to combine them as well. Let's subtract 5% of S over here, the 0.05 S. If I subtract 0.05 S here, it goes away. If I subtract 0.05 S here, well, what's 0.07 minus 0.05? If I have 7 pennies and I subtract 5 pennies, I'm left with 2 cents, or again, 2 cents, 2 out of 100, or 0.02. In order to solve for S here, let's divide by 0.02. So we can go to our calculator, 300 divided by 0.02. Another way I like to look at this, 0.02 is the fraction 1 over 50. So if I did have 1 over 50, right, that's the same thing. 0.02 is 1 out of 50. And if I wanted to get S by itself now, S by itself, since I'm multiplying by 1 over 50, I can get rid of that by multiplying by 50. And as you see here, 50 times 1 over 50, well, that's just 1. 1 times S is just going to give us S. 300 times 50, 3 times 5 is 15. How many zeros do we have? 1, 2, 3. So whether you multiply 350 or go ahead and do 300 divided by 0.02, they want to know how many times can 2 pennies go into 300? 15,000 times. So what is this telling us here? What did we solve for? We solved for X. This right here, point of intersection, is telling us here, it's saying, what does this point of intersection signify? In part B, what does it signify? If S equals 15,000, it means that it doesn't matter what your initial payment is here, whether they give you 2,000 or 2,300. If you do $15,000 in sales, whether for your current job or your new job, if you have $15,000 in sales, you're going to get paid the same regardless. Whether you get paid over here at 7% commission or you get paid here at 5% commission. If you do $15,000 in sales, you will get paid the same for each company. And we can check and see, well, how much is that? What is 7% of 15,000? We'll check that and then add it to 2,000. It'll be the same as 5% of 15,000 plus 2,300. In part C, it says you think you can sell $20,000 worth of a product per month. Should you change your job? Well, what we can do there again, just take the 20,000 and plug it in for S and see which one's higher. But again, what does this break-even point tell you? It's telling us that in the long or in the short end, right? If we sold nothing, let's say we sold 0 in sales. For my current job, I'm going to get $2,000. If I sold nothing in sales, I'm going to get paid $2,000 no matter what. Over here in my new job, if I sold 0, I'm going to get paid $2,300 no matter what. However, if I do start to sell stuff, my break even is 15,000. It says it doesn't matter which job you work at. If you sell 15,000, you get paid the same. But what the break even tells us is if I sell less than $15,000, then which job am I going to get paid at more? Let's say if I only sold $10,000 that month, which job will pay me more? That's what the break even is helping us. Look at the graph. Graph these two lines. Graph these two lines. and see which one's higher on the graph. That's the one you want to go for. But what the break even says is if your sales are less than 15,000, you're actually going to make more money over here. That front end is going to help you out so much more. That extra $300 at the front. But what the sales commission says is the better seller you are, the more commission you want. I would rather have 7% than 5. I'm going to get more money on the sale. Now, of course, this is much lower than this, but if I'm a good salesperson, it might actually be better for me in the long run. If you can sell more than $15,000, you are going to get paid more over here because that high commission rate, rate's a percent, that high commission rate is actually going to get you paid more in the long run. So it says if you think you can sell $20,000, if you think so, that's more than 15. That's more than the break-even point. So part C, I would stay at my current job. If it's more than 15,000, you'll get paid more over here.